Good evening, and I'm sorry to croak at you. I'm just getting over flu, one of these things. Have you ever seen the merry dancers, the Northern Lights, Aurora Borealis? They can be lovely. We don't often see them well from here, but you do from further north. So Chris Lintott and Pete Lawrence went to Tromso in North Norway.
About half an hour's drive out of Tromso is the Eyken radar facility. It's mid-January and the weather up here is rather mixed. A warm day is -5 and it can get as cold as -25 degrees centigrade. If it stops snowing, we hope to see something rather special, the merry dancers at play. Scientists from all over the world come to this part of northern Norway to study the Aurora Borealis, the northern lights. We're in the Arctic Circle here. The sun hasn't risen properly for more than a month. But nonetheless, this is the place to come if you care about what happens high above our heads in the Earth's upper atmosphere. These pictures, taken from the space shuttle, show the aurora in the ionosphere, the very top of the Earth's atmosphere. Here, high-energy particles from the sun excite atoms in the atmosphere, making them glow. The magnetic field guides the particles towards the poles, creating a ring of light, the auroral oval. Eyken is positioned right beneath it. Dr. Mike Rietveld is the senior scientist here at Eyken.
This is the big antenna which we use for studying the aurora in the upper atmosphere.
In something called the ionosphere, I know. So what's the ionosphere? Where is it?
Well, the ionosphere starts at about 80 kilometres and goes up many hundreds of kilometres. It's really a region of space through which many satellites and the shuttle flies.
So it's the real upper region of the Earth's atmosphere, and that's where we see these northern lights, the aurora. So what's special about the ionosphere?
Well, it's the upper atmosphere, so it's where the air molecules get very thin, and then sunlight, or the ultraviolet light from the sun, can split off the electrons from the ions.
So you have charged particles, negative electrons and positive ions.
That's right, yes. But it's basically, as you say, energy comes from the sun, and it makes the electrons very energetic. And then they come down and hit the atmosphere, and it gives light, a bit like a fluorescent tube.
What's the main sort of research that Eyken does here?
Well, it's pure research, understanding the upper atmosphere and understanding the physical processes associated with the aurora, but it has implications maybe for communications, satellite communications to the ground, because the ionosphere affects all radio waves.
We bounce radio waves off it, in fact, or we did before satellite communications took over.
That's right. The ionosphere was very important for shortwave communications, and it's still important, but even in the age of GPS, it affects the signals a little bit. So that navigation by GPS can become a little bit more inaccurate when there's strong aurora.
How does a typical night unfold? Do you wait for the aurora to appear above the clouds in this case, or are you doing something else entirely?
We don't usually start things spontaneously, but sometimes we do if there's a very spectacular event suddenly happening. So we schedule the radar, run for some hours, and usually hope that something interesting happens, that the aurora appears. Of course, we schedule it to be at the times that are likely. Most of the time it's a bit boring, or you're waiting for something to happen.
Eyken's Tromso facility sits deep within the Arctic Circle, and on any clear night there's an 80% chance of seeing an aurora. Even if the snow ruins my chance of seeing anything, the scientists will still have data from the radar, which can try to look through the cloud and through the snow. This enormous reflector sends pulses of radio waves up into the sky. Most will escape, but a small fraction will be reflected downwards to be collected back at the dish. The radar observes the aurora for most of the year, but the really exciting times are when the sun does something dramatic. Coronal mass ejections are enormous contortions on the sun's surface, which send vast quantities of material out into space. If one happens to hit the Earth, it can cause havoc, knocking out essential satellites. In 2003, a CME, the Halloween storm, hit Earth, blinding the SOHO satellite on its way. The resulting aurora could be seen even from the south of England, providing a beautiful, majestic sight to make up for the chaos up above. Pete has been imaging Aurora whenever he can from his home in Selsey in West Sussex. He too caught 2003's Halloween storm on camera. Well, Pete, if it does clear up and stop snowing, what should we expect to see?
Well, I have had experience of coming to Tromso and seeing an auroral display in the past. I've seen a couple of displays. One was particularly faint and quite difficult to see, and basically that appeared as rays, if you like, in the sky that appeared and then just disappeared away again. But on the previous night, which was Valentine's Day 2007, I can remember seeing an auroral band going through the constellation of Orion in the south. It wasn't doing particularly much at that time, but then it started to twist into curtains, and we had rays, which are just pillars of light, if you like, coming off the band.
And what about colours?
If it's a weak display, there's not enough light to stimulate the colour sensors in your eye.
So in the same way that most stars look white because they're too faint to show colour.
That's right, and what you see basically is a sort of monochrome display. But if it's bright enough, the first sort of colour hint you get is green, which is due to excitation of oxygen.
Reds as well sometimes?
There's a red you can get on top of the green, which is often linked to a very weak display, which is again due to oxygen. There are also blues and purples in there as well, which is due to excitation of ionised nitrogen.
How bright should we expect these aurorae to be?
Again, it really depends on the display itself. I mean, the aurora can be intensely bright. I mean, it can cast shadows, and there are reports of a particularly brilliant storm where people were actually reading their newspapers by the light of the aurora. But quite often it's fairly faint.
So it's important, therefore, to get to a dark site and to give your eyes time to adjust.
Definitely. Any stray light around will take your attention away from it, and if it's a particularly faint aurora, you won't see very much. And that goes for moonlight as well, of course. If the moon is up and the aurora is faint, it'll tend to drown out any display there.
Well, that's one thing we do have in our favour. No moon tonight, so if it does clear, conditions are good. Pete, thank you very much.
Thanks, Chris.
Scientists at IceCat have resorted to creating their own aurora, turning the entire ionosphere into an experiment by bombarding it with radio waves. The effects are small, but it's the first step to unlocking the secrets of the merry dancers. Mike Koch and his collaborators are here on a mission. Starved of information about the upper atmosphere, they're sending rockets up to trace the movements of the ionosphere.
Basically, space weather is in its infancy. So the analogy for that is, how do you predict the weather if I give you 12 thermometers and you have these 12 thermometers all moving around on the planet of the Earth, but yet you still want to predict the weather on the Earth everywhere.
And that's the only information you've got, yeah.
At this time.
So tell me about the rocket campaign. What role do rockets have?
Rockets has a very special contribution because it covers a part of the height range in the atmosphere which is not accessible directly by satellite or from the ground. So once you're about 20-30 kilometers, you can't go with an aircraft or a balloon. And once you're below, say, 200 kilometers, you can't do an in-situ measurement by satellite. So a rocket would allow you to sample what's going on in situ.
And I know you're working on a rocket campaign that's happening here right now. What are the goals of that program?
The main goal of that program is to launch a rocket that will launch up to 150 kilometers, and then as it flies down, it will release a chemical called TMA, trimethyl aluminium, and that burns in air, in oxygen, and glows. That cloud of glowing gas will move with the neutral wind. So we're going to puff at 4-second intervals from 150 kilometers all the way down to the ground, and then using cameras in multiple sites, we're going to track those glowing clouds. And the key here is we want to measure not only the horizontal winds in that part of the atmosphere range, but also the vertical winds, which is the reason why we have this puffing action.
To see the rocket's trace, Mike also needs a clear night. It's 4 o'clock in the afternoon, and up here in the Arctic Circle it's already pitch black. The bad news is that the weather's still pretty bad, the forecast is worse, so we're going to need an awful lot of luck if we're going to see the Northern Lights tonight. I'd just about given up on seeing anything, and then the clouds parted. Suddenly, the aurora came out to play. It started gently, barely visible to the eye, but in these speeded up pictures, you can definitely see the movement of the Northern Lights. In the distance, the pink glow of Tromso only adds to the picture. Pete and Mike Kosh joined me outside to watch and photograph the display. To avoid disturbing our view of the sky, we've switched to an infrared camera. Local Aurora chaser and expert imager Chetel Skogley also kept us company. Well, this is pretty spectacular. This is the brightest I've seen Aurora for a long while. How quickly can things alter?
It alters really quickly. Yeah. It can be go so fast that yeah, you can't imagine it. You have to see it.
As we're doing now. Look at these
brightening over there, isn't that fantastic?
Low down, and these vertical lines. Mike, what's causing this structure? It's not just a simple curtain anymore.
No, the vertical lines, they basically are always parallel to the Earth's magnetic field. So the particles that come down, that collide with the atmosphere, that cause the aurora, are guided by the magnetic field. So you're seeing the magnetic field structure, and then the vertical extent is due to the fact that the aurora doesn't occur just at one altitude. Mm-hmm. It typically occurs from about 100 kilometers at the bottom to 200 or 300 kilometers at the top.
Okay.
And that's due to the fact that the energy of the electrons that are coming down is not a single energy. Uh-huh. There's a spread of energies. Higher the energy, the lower the altitude, typically.
Okay. So how long have you been chasing the Northern Lights?
Since 29th of October 2003.
Now I know that day. We saw that in England, in fact. So it must have been good. How did it look from here?
Oh, it was amazing. You could actually see the snow was colored red.
Wow.
Yeah. It was the first night out there and the best night. So I just had to close the door and start all over again.
And then you started taking images.
Yeah.
I mean, I've seen some of your work. How on earth do you produce those? Because we were arguing about it. And we decided we should just ask you.
It's hundreds of stills. I put them together with transitions between.
Wow, look at that.
It's quite spectacular.
It is.
So, Mike, what would the radars be doing right now?
The radar is fundamentally measuring the actual electron density, the plasma density as we call it, and the temperature. There's more energy being dissipated in the atmosphere from the auroras than there are all the power stations on the planet put together. So the energy that's being dissipated is fantastic. The problem is, of course, it's mostly at least 100 kilometers above our heads. So if we could gain access to it, it would probably solve our energy requirements forever. But unfortunately, it's a bit difficult to get your plug up there 100 kilometers above our heads. So
the whole sky seems to be glowing now. Is that my eyes, or is that?
No, I think it is definitely. There's it's actually moving down to the south, isn't it? Some of it is just above Orion, and we've got a good brightening over there in Leo now as well.
Yes. Oh, look at this! Amazing. Look at that! It's very faint, incredible. But there are these dark lanes, almost as if they've been drawn through the sky.
Yeah.
It's stunning. These aren't the black aurorae.
They could well be. You have these lanes between the aurora, which are almost completely devoid of the aurora. They're not quite empty. And that's the region where the currents that are associated with the aurora flow back out into space.
It's quite an eerie effect.
It is. It's amazing, isn't it?
Yeah.
We've got a brightening edge now appearing up there. Look.
That's one of the mysteries of the aurora, is why it's possible to have structures that are so thin. That's very hard to explain. It's much easier to explain the 1,000 kilometers of east-west extent, but when you have these very thin structures, generally in the north-south direction, they are very hard to explain.
So I guess we've had the scientists view from Mike. There must be all sorts of legends. I can't imagine living out here and seeing this and not inventing stories. What are the local stories about the Northern Lights?
The Vikings, I think they call it the bridge to heaven or something like that.
Okay.
And,
isn't there a rather lovely Danish legend about swans that get trapped in the ice, and it's them flapping their wings and reflecting the light, which is causing the Northern Lights?
Yes.
It's also a myth about unmarried women who died, and they're still floating up there, releasing energy.
More energy than all the power stations, apparently.
Oh, yes.
That sounds lovely.
In fact, it's absolutely brilliant.
Well, the show seems to be over. We had streamers, we had bright bands, we even had the Aurora overhead, which I've never seen before. It's been literally unforgettable. A few weeks after we filmed, Mike's rocket campaign had a successful launch. In this fisheye view of the entire sky, you can see it tracing the movement of the upper atmosphere, the home of the Aurora.
Well, I had a good time in Norway. I wish I'd been there. But I'm joined now by two experts, Professor Tony van Eyken, former director of IceCat, and Dr. Chris Davis, who's deeply concerned with stereo. Tony, may I come to you first? We know exactly how the aurora is caused now.
We do, in general terms. The processes that make the light in the atmosphere are actually exactly the same processes that make fluorescent tubes work.
Yes.
What's more interesting is the source of the particles that cause that. And although we know that in general they come from the sun, something must add energy to them before they arrive in the atmosphere, because the interaction that's necessary to produce that light is much more energetic than the energy of the particles in the solar wind.
These solar wind particles are charged, and therefore they tend to go to the Earth's magnetic poles.
That's right. Because the solar wind is blowing from the sun and arrives and finds the Earth's magnetic field there, it actually has to divide and go around it, so the Earth is a bit like a rock in a river from the point of view of the solar wind. And the particles in the solar wind can get into the Earth's magnetic field out there in the geomagnetic tail, and they get accelerated and come down the field lines and crash into the neutral atmosphere and produce this beautiful light.
They can be really spectacular, but of course they do depend entirely upon the sun. And of course that's your province, Chris.
Yes, well we know now that the sun is not a very stable star. It is variable. It has an 11-year cycle. And as a consequence of that, the sun emits storms into space at different rates. When the sun's very active, you get a lot of storms being emitted from the sun, and when the sun's quiet, you get much fewer.
Solar wind.
And the solar wind is blowing out from the sun constantly, but the rate at which the particles come away does vary. And now the stereo mission was launched in 2006 to actually look for storms in the solar wind that are actually heading towards the Earth. We have two spacecraft, one just ahead of the Earth and one lagging behind, and these provide a stereoscopic view of the sun and the space in between the sun and the Earth. So during the period that the Sky at Night team were at IceCat, we were able to look with the stereo cameras to see what was coming towards the Earth in the solar wind.
What was?
Well, I can show you now on the movie here. I'll just explain what this picture is. This is one of the images from the heliospheric imager, which is a camera mounted on the side of the stereo spacecraft, and it looks back between the sun and the Earth to see what's coming earthward. So the sun in this picture is just off the frame to the right, and the bright blob in the middle is the planet Mercury. And you can see that there's a lot of material coming off the sun. And in the middle of the month here, there's a mass ejection there which washes out through the solar system. And we believe that these storms are the things that influence the Earth's space environment and precipitate the aurora.
We're nowhere near the peak of the solar cycle yet, though.
No, we're at solar minimum, very much minimum.
Yes.
This is about as quiet as the sun gets.
Yes.
So it's actually very good for studying these mass ejections because they're occurring in isolation, and we can study the formation of them and the propagation through space. So for the very first time with stereo, we can actually detect not only the speed of these mass ejections, but we can actually tell you which direction they're going in. And we're working towards providing a space weather forecast, because these are a significant radiation hazard if you're an astronaut in space or if you're operating a particularly sensitive instrument on a spacecraft.
We get southern lights too.
Yes, the Earth's
enjoyed mainly by penguins.
Yeah, the Earth's magnetic field is, of course, we're very familiar with having a North Pole and a South Pole. And although we see the aurora over the North Pole more often, there's more landmass there for people to observe it from. Simultaneously, you get what's known as conjugate aurora. So you tend to get very similar features in the aurora on both poles of the planet.
There are also detailed differences, and so actually if we can study the aurora in the southern hemisphere as well, then that will give us a much better understanding of how the interaction between the solar wind and the Earth is.
And of course, other planets. Mars,
Well, the aurora has been observed on Mars, but it's in a very localised context, exactly, because Mars doesn't have an active magnetic field like the Earth, but it does have a remnant magnetic field. Observations have revealed that there are still magnetic structures preserved in the rocks, and those produce what scientists are calling mini magnetospheres, little mini magnetic bubbles. And of course, those can concentrate the solar wind as it penetrates the Martian atmosphere and generate little localised auroras.
And of course, the outer planets, Jupiter and Saturn, there are lovely aurorae there.
Yes, I mean, we've got some lovely photographs from the Hubble Space Telescope showing the aurora on Saturn and on Jupiter. So any planet that has a magnetic field and an atmosphere and is sitting in the solar wind should generate aurora.
It's fair to say we don't know everything about aurorae.
Oh, that's really true, yes. Although we understand in general terms why the aurora should form where it does and why it generates light in the way that it does, our understanding would tend to produce rather smooth aurora in just ovals around the pole. When you eventually go there and you see it, you'll see it's a very much more complicated structure. There are these intertwining fields, waving curtains of light, and that we really don't understand. That fine detail we don't understand at all, yet.
Well, the aurora is certainly worth seeing. Tony, Chris, thank you very much.
Thank you.
Thank you.
What else? Now we have a comet coming, Lulin's comet. And Pete Lawrence, still in the far north, is going to tell us where to find it.
A snowball and a comet actually have quite a lot in common. In fact, if you add some dirt and grit and some rather nasty frozen gases in there, you've got a pretty good model of what a comet is. Of course, the real thing is actually a bit bigger than this, anywhere between 100 metres and, say, 40 kilometres across. They exist in a region outside of the planets, in the far extremes of the solar system. And occasionally, one of these dirty snowballs will come flying in towards the sun. When this happens, as it gets closer to the sun, some material gets thrown off the comet and ends up in a shroud, if you like, around this nucleus. And it's this shroud that reflects sunlight back, and that's what we can see actually as a fuzzy comet in the night sky. Now, throughout February, we've got a comet which hopefully will become naked eye visible. This is Comet Lulin. It's a new comet. It's coming from the outside of the solar system on an open orbit. It'll come around once and then it will disappear again. And it has the virtue of being quite easy to see in the last week of February. So let's see how we can find it. To do this, we have to use our old friend, the plough, or as I prefer to call it, the saucepan. If you imagine it as a saucepan, pick the two stars which are furthest away from the handle. Those are called the pointers. They point up towards the pole star, Polaris. Now, the two stars next to the handle, I like to think of as the reverse pointers. If you point them down, you eventually come to a fairly bright star, which is known as Regulus, and that's the brightest star in the constellation of Leo the Lion. You know if you've got the right star because above it there is a question mark, a backward question mark of stars, which is known as the sickle. Now, below and to the left of Regulus, there is a fairly brightish yellowish star, which isn't a star at all. That's the planet Saturn. And Saturn and Regulus are the two markers to finding Comet Lulin throughout the end of February. On the night of the 23rd, the comet could be found 2 degrees below Saturn, to the south of Saturn. That's 4 full moon diameters below Saturn. So if you've got a pair of binoculars and you can find Saturn, place Saturn at the top of the field of view, and there at the bottom you should see a little fuzzy patch, perhaps even with a tail, and that's Comet Lulin. On the night of the 27th, the comet actually passes just 1/2 degree to the south of Regulus, and that makes it extremely easy to find. So if you put Regulus in the field of view of a pair of binoculars or even a telescope with a low power, you should be able to see this fuzzy blob, this fuzzy patch, which is Comet Lulin. Now, will it make naked eye visibility? Comets are very unpredictable. All we have to do is hope that something exciting happens with Comet Lulin, go outside and see for yourselves.
Well, we'll wait and see what Comet Lulin will do. One never knows with comets. And now, on to our news notes. Chris, methane on Mars. Well, we know about that anyway. Mars Express found it, but now we found it's localised, and that's Very interesting.
Methane, carbon with some hydrogen stuck to it, is very interesting because it shouldn't exist in large quantities in the atmosphere of Mars. It does. It should be destroyed quite quickly. So that tells you that there must be a source of methane somewhere on the surface. Now, we don't know what that source is. It could be volcanoes. It could be some unusual chemistry, or it could be bacteria. We don't know what the source of the methane is. We've known it's there since 2004 when the European Mars Express probe detected it. But Mars Express is quite a crude instrument, really. It's not their fault. They did the best you could put on a spacecraft, but it can only measure the overall concentration. Whereas these new results from scientists using a couple of telescopes on Mauna Kea in Hawaii tell us, first of all, that the methane is associated with particular points on the surface. Nil Fosse, for example, this wonderful channeled region, has a particularly high concentration, and also that the amount of methane changes over time. It changes with the Martian seasons, in fact. Now, I'm not sure what those two pieces of information tell us, but it's the first step in trying to work out where this methane is coming from.
This does not prove there's life on Mars, but I think on the whole, it does make the idea of primitive Martian life rather more plausible.
Yes, and it's certainly true that life is as good an explanation as anything else for this signature.
Well, I've always been 50-50 about life on Mars. I think now I'm going to say I'm 60-40.
Well, maybe. We can't rule out the idea that there's some volcanic activity under the surface. But, you know, even that's interesting. If Mars has complicated volcanic processes going on now, that's fascinating. If it's unusual chemistry, then that's interesting. But it could just be life.
We must wait and see.
We must. We need to find out where this methane is coming from.
And, of course, the Mars rovers are still going strong.
Yes, we can't talk about Mars without talking about these marvellous machines. They've just passed their 5th Earth year on the Martian surface. It's been unbelievable. Opportunity is heading 12 kilometres towards a crater called Endeavour. It's a long way away. It's a long shot as to whether Opportunity will ever make it, but it's already covered a kilometre of the ground. So fingers crossed that in 2 years' time, would you believe, Opportunity is expected to arrive at Endeavour. So let's hope it makes it.
Now let's go beyond the solar system. The Milky Way. How big is it? Well, bigger than we thought.
For starters, it turns out we're moving faster than we thought. The Sun orbits the centre of the Milky Way, as all the stars in it do. We thought we were moving about 500,000 miles per hour. Actually, turns out we're moving at 600,000 miles per hour. And the reason for that is the Milky Way is more massive than we thought. It's about half as big again as previous measurements indicated.
And how does that tie in with the Andromeda galaxy?
Well, it almost puts us in first place, because it means the Milky Way and Andromeda, the other big nearby galaxy, are about the same size.
Exactly.
And it also means the two are much more likely to collide. We've always thought that in a few billion years' time, the two big galaxies in the local group, the Milky Way and Andromeda, will hit, producing a spectacular collision, which will really be worth looking out for. The fact that the Milky Way is more massive than we thought means its pull is greater, and that means that the collision is all the more likely.
I'm afraid the Earth won't be there by that time.
No, but we'll report it on the sky at night. It'll be fine.
Chris, thank you. It's newsletter time. So if you want your newsletter, send your stamped addressed envelope to newsletter 112, The Sky at Night, BBC, Birmingham, B1 1RF. And so, until next month, night.
Next tonight on BBC4, pitting literary minds against each other in a war of words. Kirsty Walk hosts another edition of the Book Quiz.